All right, let's talk about something that sounds super intimidating: general organic chemistry. But trust me, it's not just some tough subject. It's basically the secret language of life itself. So let's crack this code together, one step at a time.
I mean, think about it for a second. How can one tiny little atom be the foundation for the entire living world? It's kind of mind-blowing, right? Everything, your DNA, the food you just ate, it's all built around this one amazing element. So let's figure out what makes it so special.
And here it is, the star of the show, carbon. You know, when we talk about organic chemistry, we're really just talking about the chemistry of carbon. It truly is the backbone of life. But what's its secret? What's its superpower?
Okay, so here's the deal. Carbon's magic is all about how incredibly versatile it is. First off, it can form these super strong, stable bonds, both with itself and with other elements. And from there, it can go wild. It can build these long, straight chains, or it can make these complicated branching structures. It can even loop back and form rings. It's like the ultimate Lego brick of the universe. You can build pretty much anything with it.
But just saying it's like a Lego brick isn't enough. To really get how it builds all this cool stuff, we've got to look at its secret weapon, this kind of shape-shifting trick it does. And this is a huge concept. It's called hybridization. Honestly, it's the key to understanding everything else we're going to talk about.
So, what even is hybridization? Well, think of it like this. Carbon has these spaces where its electrons hang out, called atomic orbitals. Hybridization is just the process of mixing those orbitals together, kind of like a DJ mixing tracks, to create brand new, perfect orbitals that are just right for making super stable bonds. Okay, first type. It's called sp3 hybridization, and the name tells you exactly what's happening. Carbon takes one s orbital and three p orbitals and mashes them together. What do you get? 4 identical sp3 orbitals. These 4 new orbitals spread out as far as possible, forming this perfect tetrahedral shape, which is just what you need to make 4 strong single bonds. The classic example? Methane. Now this is where it gets really interesting. sp2 hybridization. See, this time, carbon only mixes 2 of its p orbitals with the s orbital. That gives you 3 new sp2 orbitals that all lie flat in a plane. But wait a minute, what about that leftover p orbital? Well, that is the secret ingredient. It's what allows carbon to form double bonds. Super important. And last but not least, we've got sp-s hybridization. You can probably guess this one. It's just one s and one p orbital mixing together. This creates 2 sp orbitals that point in opposite directions, making a perfectly straight, linear molecule. And those 2 leftover p orbitals, you got it, they're used to form a triple bond. Okay, so the bonds are formed, the molecule is built. But the story is far from over, because once those bonds are in place, a whole new drama begins. Inside these molecules, there's this constant invisible tug-of-war happening for the electrons. So this first force we need to know about is called the inductive effect. And really, it's just a permanent push or pull of electrons through single bonds. So if you have an atom that's really greedy for electrons, it's going to pull them towards itself. We call that a negative or minus I effect. On the flip side, if you have a group that's happy to give electrons away, it'll push them, and that's a positive or plus I effect. Just look at these examples here. Over on the left, that chlorine atom is way more electronegative, so it's yanking electrons away from the carbon chain. That's a classic minus I effect. And on the right, the nitrogen in that amino group, it's doing the exact same thing. And this little tug, this subtle pull, it has a massive impact on how the molecule actually behaves. All right, so if the inductive effect is a tug-of-war, the next one, the resonance effect, is way more powerful. Think of it less like a tug-of-war and more like teamwork. With resonance, electrons aren't just stuck between 2 atoms. No, they get to move around. They get spread out over the whole molecule. And by spreading out that electronic charge, the entire molecule becomes way, way more stable. And you can see it happening right here. Look at those arrows. They're showing you how electrons and charges can just flow around the molecule, like in a benzene ring. So, if you have a group that pulls electrons out of that system, we call it a negative resonance, or minus R effect. And if a group donates electrons into the system, you guessed it, that's a positive or plus R effect. Okay, there's one more stabilizing force we should know about. It's called hyperconjugation. Sometimes people call it no-bond resonance. It's basically a special case where electrons from a nearby single bond can help stabilize a problem area,
like a positively charged carbon or a double bond. It's kind of like neighboring bonds pitching in to lend a helping hand.
Phew. Okay, that's a lot of talk about invisible forces pushing and pulling electrons. So why does any of this matter? What's the point? Well, here it is. Because if we understand these forces, we can do something amazing. We can predict what a molecule is going to do in a chemical reaction. This is where all that theory turns into a seriously powerful tool.
So, the big question is, how does knowing about this constant electron tug-of-war actually help us? Well, let's look at one of the most basic, no pun intended, properties in all of chemistry: acidity and basicity.
Turns out, these effects are exactly what determines how acidic a molecule is. This table here is basically our rulebook. Look, resonance is a massive factor. It boosts acidity because it helps stabilize the molecule after it gives up its proton. A strong electron withdrawing effect, the -I effect, also increases acidity. And yeah, even the hybridization matters, with sp being the most acidic of the bunch.
This right here is a perfect example. Just look at these two molecules. Now, why is the one on the right so much more acidic? Well, it's got those 3 chlorine atoms, right? Each one of them is pulling electron density away with that powerful -I effect. That pull makes it way easier for the molecule to let go of its proton, and it makes the leftover part much more stable.
So what about basicity? Well, it's pretty much the complete opposite story. If you want to make a molecule more basic, you need to pump up its electron density, make it really eager to grab a proton. So it makes sense that electron-donating groups and the +I effect both increase basicity. And yep, the hybridization trend is flipped on its head too. sp3 carbons are the most basic.
Okay, let's boil all of this down. Time for the final cheat sheet. If you're going to remember anything, these are the key points you need to have in your back pocket to predict chemical behavior like a pro.
Let's go. Quick fire round. Electron withdrawing groups, they increase acidity and decrease basicity. Simple. Electron donating groups, they do the opposite, increase basicity, decrease acidity. And for hybridization, just remember that the electron-rich sp3 carbon is more basic than an sp2 carbon. Got it? Good.
But this slide right here, this might be the most important takeaway of all. This is the ultimate tiebreaker, the hierarchy of power. Because what happens when these forces are competing against each other, right? Imagine one group is pushing electrons in through resonance, but another is pulling them out with the inductive effect. Who wins that fight? Well, here's the answer. Resonance is king. It's the trump card. It always wins. After that comes hyperconjugation, and then last place, the inductive effect. This hierarchy is the key to solving almost any puzzle.
So there you have it. We've pulled back the curtain on how carbon structure and all those invisible forces totally dictate how it behaves. You now have the rules of the game. You know the code. So the only real question left is, what molecule are you going to go analyze next?